Aloha champions, and welcome back to another science video. It's the only one we have for this week, but it is a fun one. Today we're on chapter 5 of unit 1, energy transfers and transformations, talking about how collisions can transfer energy. So before we get too far into our chapter today, think about the big question of the day. How is energy involved in collisions? And before we answer this big question, we have to learn, what is a collision? So down here in our vocabulary, to collide is to come together with impact. So the verb here is to collide, to come together with impact, okay? A collision is the noun. It's an instance of colliding. So when two things come together in an impact, they collide and we have a collision. In both of these words, collide and a collision, the word part col means together or with. Okay, so they come together, col. They collide to make a collision. All right. Clap your hands. When one hand hits the other, your hands collide. Lift your foot and then stomp down to make it collide with the floor. And I'm sorry for the first grade teacher below me who's probably making a video herself. I'm sorry. Roll two toy cars down ramps towards each other and watch them bang into each other. That is a collision too. A collision happens when two objects make contact. In every collision, changes occur. You might see objects change the speed or direction of motion or even change shape because of a collision. You might hear a sound or see sparks from objects colliding, or you might feel an object colliding with you. If you've ever played tag and somebody runs into you and tags you, they're colliding, they're making an impact with you, okay? So collisions involve changes in motion. Moving objects have energy of motion, kinetic energy. And in any collision, at least one object is moving. You have to have one object moving. Something can be staying the same in case you've ever ridden your bike into a curb or something like that. But one object is moving, okay? And we know that energy is involved in collisions because collisions result in changes. If you've ever been in a car accident, I hope you haven't, but sometimes it happens, you know that big changes happen from that, okay? And when we have change, we have energy because energy causes change. A bowling ball has motion energy, kinetic energy, as it rolls along the lane toward the pins. What happens when the bowling ball crashes into the pins? Can you predict how the pins will change if I roll a bowling ball down the alley? Well, hopefully most of them will get knocked down. But if you know me and my bowling, chances are the pins will be just fine and the ball will just roll into the gutter. But that's me. You're probably a better bowler than I am. Before the collision, the pins are sitting still and not moving. The collision with the bowling ball changes that. The ball strikes the pins, and some of the ball's energy of motion, kinetic energy, transfers to the pins. So when the ball hits the pins, it's taking its energy and transferring it to the pins to hopefully knock them down. Okay? This makes the pins gain motion energy, kinetic energy. So kinetic energy to make something gain kinetic energy, and leaves the ball with less motion energy. The collision between ball and pins also produces a loud noise, crash, onomatopoeia, and this is one of my favorite chapters because I'm going to say that word a lot. Yes. A change in the form of energy from motion to sound. So you have motion energy moving. You also have sound energy caused by the collision. A lot of changes are happening when things collide. What would happen if two bowling balls smashed into each other from opposite directions? From the right to the left, if I had two bowling balls, what would happen? Well, the colliding balls would bounce off of each other, changing their motion. So they'd meet in the middle, and then they bounce backwards or in different directions. They'd collide and change directions. The colliding balls would bounce off of each other, changing their motion. The speed and direction of each ball would change. The energy of motion, kinetic energy, would cause changes during this collision. Sometimes, a collision can change an object's shape. An object in motion has energy. In a collision, that energy can cause many kinds of changes, not just changes in motion or sound. Imagine you have a lump of clay rolled into a ball the same size as a baseball. You throw the clay hard against a brick wall, splat. The collision doesn't set the wall in motion. You can't knock over a wall with a lump of clay. So a change has to occur. And will that change? The energy of motion causes a different change. First, the motion of the clay ball stops. Second, the shape of the clay becomes as flat as a pancake. So as it's coming in, it's shaped like a ball, hits the wall, and it will splat. It will flatten out. Okay? Think again about two colliding bowling balls. They are hard enough that they can roll into each other, bounce apart, and have their shapes probably remain unaffected, unless you're a really powerful bowler, and then you might chip something, but that's rare. But think about an egg that is dropped, and when it collides with the floor, the shell shatters, and the liquid inside splatters into a mess. This is a change in shape. So every time you crack open an egg, you're changing its shape through the power of a collision and transferring the energy of your hand to the egg, to the bowl, to break it apart and change its shape. Engineers design cars to protect passengers during a crash. Cars are designed to limit the damage to people that might occur due to a collision. The car in this picture is built so that the front part changes shape more easily than the parts closest to the passengers. This design is on purpose. Less of the energy from the collision is transferred to the passengers, better protecting them from energy. So see how this hood of this car is all bent up like that because of its collision? Well, it's supposed to crumple like that because it protects you. It might be costly to repair, it might total the car, but you are still safe and can walk after a car accident like that. So engineers have looked at energy transfer through collisions and have tried to do their best to make it so you are safer. Okay? This is my favorite page. Yeah. Many collisions make sounds. Clap. Two hands collide. Crash! Two cars collide. Crack! A baseball and a bat collide. Splat! An egg and the floor collide. Boom! A mallet collides with a drum. Collisions often produce a sound, as well as changes in motion and shape. When objects collide, some of the motion energy causes vibrations in the objects. Did you see all that onomatopoeia in there? It's so great. Clap, crash, crack, splat, boom. Perfect uses of onomatopoeia. But before I get carried away, we have a new vocabulary term that was introduced on this page. Sound. A form of energy that comes from a vibrating object. A form of energy that comes from a vibrating object. When I'm talking, It's my lungs vibrating my tongue and coming out as airwaves. As you're listening to this on your device, it's a speaker, and that speaker is vibrating air so that you can hear the replication of my voice giving you this lesson. So sound is a form of energy that comes from vibrating objects. If you hit something and it vibrates, it might make a noise. All right, where was I? Too much onomatopoeia, too much excitement about energy and collisions. These vibrations also cause the air to vibrate. Those vibrations transfer energy to our ears. We sense this transfer of energy as sound. When two objects collide, the energy of motion causes changes that result in the energy of sound. So here we have a drummer. He's got his mallet and his big drum. The collision between a mallet and a drum makes a big sound. The shape of the drum transfers much of the energy from the collision into the surrounding air, and we detect that as sound. Think about space. Collisions in space don't make sound. There is no air in the vacuum of space, so there are no particles of matter to be affected by the vibrations of the collision. Without matter surrounding the colliding object, sound energy cannot move away from the vibrating objects. So even though things might collide in space, little bits of meteor hitting the International Space Station, it doesn't make a sound, or at least not outside it would. For the astronauts and cosmonauts living on the International Space Station, they might hear it because they have air, but outside there's no air, it's a vacuum, and so the air can't vibrate and send sound to you. No sound in space. It's an interesting thought experiment. Speed affects collisions. Speed is how fast an object moves to get from point A to point B. In previous chapters, you learned that the speed of an object is related to its motion energy. How much kinetic energy it has is how fast it is moving. It is not surprising that the speed of moving objects affects the kinds of changes that occur during some collisions. In the game of water balloon toss, the goal is to keep throwing the water balloons back and forth without breaking them. Sometimes they do go splat and we're drenched, but the goal is to keep it up in the air as long as possible without it splatting. The winners know they need to toss the balloons gently and catch them carefully. Throwing a water balloon faster produces a harder collision. Greater energy transfer from the balloon's motion stretches the thin material until it tears and the water gushes out. An object moving at faster speed has greater energy of motion than the same object moving at slower speed. The object transfers more energy in a collision when it is moving faster than when it moves more slowly. The faster it moves, the more energy it has to transfer in a collision. At a slower speed, there is less energy of motion that can be transferred. So here we have a demonstration. This young man is throwing a water balloon. It hits the tree and bounces off. It was a soft, gentle pass. Here, he's chucking it. It's overhand throw, and it goes splat. So the softer you throw it, the less likely that collision's going to cause a whole lot of change. But if you throw it real fast, you can cause a lot of changes. Weight affects the changes caused by collisions. Getting hit by a flying cotton ball is silly fun. If anybody's tossed a cotton ball or marshmallow, it doesn't hurt. It just... But getting hit by a flying rock is a different story. Even if the cotton ball and the rock are the same size and moving at the same speed, the rock has greater energy of motion, more kinetic energy. Why does it have that? Because the rock weighs more. An object that weighs more has more energy behind it. So the rock has more energy of motion, kinetic energy, than the cotton ball moving at the same speed. Weight affects the energy of collisions. Each moon crater offers evidence that motion energy during collisions causes change. Objects in space, such as meteoroids, have been crashing into the moon's surface for millions of years. The heavier these moving space rocks were, the more motion energy they brought to the collisions with the moon. Heavier meteoroids produce deeper craters than lighter meteoroids traveling at the same speed. So, while the Earth has its fair share of meteors that hit Earth or burn up in our atmosphere, the moon doesn't, and it holds every scar from every meteor that's hit it. And the heavier it is, the deeper the impact it would create. The lighter it is, the smaller it is, the smaller of a crater it will make. Okay? So the faster or the more heavier an object is, the more kinetic energy it has and the more potential to cause damage during a collision. And with that brings us to the end of chapter 5. There are 5 to 10 questions for you to answer in Google Classroom. Thank you for watching this video. You stay awesome. Do your best on the upcoming map tests, and I'll see you real soon.